Hi, my name is Thea Spellmeyer, and I'm a sophomore studying chemical engineering and biomedical engineering. And my research focuses on two approaches to measuring cartilage strain in vivo, specifically the articular cartilage in the knee. So here's an image of an MRI scan of a knee, and the cartilage that I focused on is this femoral cartilage wrapping around the femoral condyle and that tibial cartilage right across that tibial plateau. Articular cartilage is important because it encases your bones right around your joints and helps your joints support weight and is what allows them to glide and move past each other. Throughout the day, you load your joints, and this causes your cartilage to compress. This compression is also called strain. Excessive strain on this cartilage can lead to damaging it and ultimately degeneration. There are two methods to recover this compression. The first method is pretty well known. It's called passive recovery, and this just involves unloading, so maybe lying supine. A new method that's a bit undocumented but being explored is active recovery, and this is the process of recovering your cartilage through walking or movement. The objective of this research was to evaluate cartilage strain in response to different loading and unloading tasks using a 1D and 3D approach. So there was a cohort of 8 healthy young adults with relatively no knee pain who performed a series of tasks, and following each task, there was an MRI scan of their right knee. So there was a baseline scan when they arrived, a period of static loading, which is just standing, a period of walking, that would be your active recovery, another period of standing, and then a period of unloading, which was lying supine. The research I worked on mainly focused on analyzing the first 3 scans. So the two methods that were used to measure the compressive strain is the 1D line method, which just measures the tibial femoral thickness by drawing a line from the femur to the tibia, so that bone-to-bone distance. And then the second method is the segmentation method, which is a 3D method, where you go through the frames of an MRI and trace the femoral cartilage and the tibial cartilage, and those tracings get rendered into a 3D model at the end. Another avenue that was explored a little bit with this is changing your voxel size, so subsampling, so you have a smaller voxel size. This means you can trace a bit more finely, but it takes more time. So here's an image of the line method. You can see the line drawn again from the femur to the tibia right at that main point of contact. And here's a picture of the segmentation method, a 2D tracing. Your blue is your femoral cartilage and the pink is your tibial again. For the segmentation process, after you have all of your 2D tracings, they get compiled into a 3D model as shown here. You've got your lateral compartment and your medial compartment, and the program that we used for the segmentations and for the line method is called 3D Slicer. After you have all your models, we used transforms to align them on top of each other. So here is the baseline scan on top of the standing scan. And then once they are aligned, we crop them so that we are looking at it, we can isolate the region of interest where that contact is and most of that strain is happening. For the results, so both methods indicated that there was compressive strain after that first period of standing of the static loading. And overall, both also indicated that there was recovery in that cartilage following that period of walking. There were a few discrepancies, maybe due to potential rotations in the subject's knees when they went for their second scan or third scan, but ultimately there was recovery seen here. And one other point I wanted to point out was that the 3D method ultimately found a lesser degree of strain and recovery, and this is likely due to the localization of the compressive strain. So the volume around that main point of contact that's not changing as much kind of washes out the strain measurements from the primary point of contact. This is significant. This research is significant because task strain responsive cartilage can be useful in predicting future cartilage health, maybe the risk of someone potentially developing osteoarthritis. And this research takes the first couple looks at what is the optimal approach to measuring this task strain analysis. Is it accurate? Is it reliable? And future steps include analyzing the rest of the cohort